mathematical thinking. And so for the session, we're going to be asking you to like dig into some things. We're going to do some math together. We're going to get curious and judgmental together. And as we do that, just to set some expectations, is as we make some claims and as you make statements and make some arguments either on the microphone or in the chat, um, like feel free to kind of push your thinking a bit and challenge yourself. And sometimes you can make some arguments that are maybe a position you don't normally take, but it's just for the sake of learning, you could start to take another position to understand this idea a little better. And then if we want to do some judgmental pieces, like we want to critique a bit, just remember to do so respectfully. Like it's, you could be curiously judgmental, if you will. Like, I wonder if if there's another way we could think about this, or I'm wondering if we could represent it differently. Feels a lot better than you're wrong. And that's not the way to do it. So we're going to uncover how this can unfold in elementary, middle school, and high school classes today, and hope that you walk away with a bunch of really good ideas that you could try as soon as Monday morning. So, Zach, I'm going to turn it back over to you.
Thanks, buddy. Oh my gosh, it's so great to see so many of you here today. It's exciting to be learning alongside you. We're going to start our session today with thinking about curiosity. And I'm going to invite you to just answer this question in the chat box while I kind of run my mouth for a minute here, telling you some of the background on this. But I want you to think about, what does it mean to be curious in the math classroom? And while you're thinking about that and sharing some ideas in the chat box, I just want to mention that I did just finish my first book, and it is called Curious Kids in the Math Classroom. And everything I'm going to share with you over these next 10 or 15 minutes as we kick off our learning together comes from that book. It's ideas that I've been thinking about and reading about and writing about for the last couple of years now. And thanks, Karina. It feels pretty good to be done. But we're working on the editing stages. This will be out in fall of 2026. But I'm excited to share some of those ideas with you today. So while we are doing that, I hope you're reading through the chat box over there how folks are thinking about curiosity in the math classroom. I think so often, particularly in elementary schools, we're good at getting kids curious about reading and writing and looking at books and predicting and wondering and noticing. And Mike and I have just been on a mission for most of our careers to get kids curious in the math classroom, because it belongs in there too, and it creates joyful learning experiences. So as we are thinking about curiosity in the math classroom, I'm going to start with a quick story, which is I'm going to ask you first to do a quick notice and wonder with me, because I saw this clock one day and I was instantly curious about it. So what I'd like you to do is just take a second right now and drop in any noticings or wonderings that you have about this clock. You can throw those in the chat box. Grace sees the Dr. Pepper. Yes. Oh, here we go. Yeah. Where is the 8? As an instant question I had as well. No number 8. Got Dr. Pepper in there. Some even numbers. Man, you guys are all feeling my pain on this. I was instantly, instantly thinking about this clock because, one, as someone who's taught second grade before, teaching time to young people is not easy, and this is not making it any easier, right? There's like, in my mind, there's all these things wrong with it. But I have to tell you, I saw this clock in a bowling alley right here in Olympia, Washington, where I live. This is an actual modern day picture of that bowling alley as well. It looks like it was like taken in like the 70s or something, but this is what the bowling alley looks like. And I saw that clock in there. And before I come back to that clock, I want to pause and kind of define the way that I'm thinking about curiosity. This comes from Susan Ingalls' book called The Hungry Mind. And Susan writes that curiosity is our innate human drive to resolve uncertainty. And I love that. It's exactly how I like to think about it. And that clock had me uncertain. I was like, where's the 8? Why are the 10 and the 2 where they are? Let's go back and look at it again. How in the world can an 11, 12, and a 1 fit in between those? And then where's the 3? How's that 3 going to fit in there, right? So many questions I had, and they stemmed from me being uncertain about something. So what did I do? I grabbed my phone and I went online and I asked, why is there a 10 and a 2, 10, 2, and a 4 on a Dr. Pepper clock? And little did I know it, I found out, y'all, there is a Dr. Pepper museum in Waco, Texas. What's up to you? Those of you that don't know about this, you should go check it out. But as I was reading about this, what I found out was that Dr. Pepper's original slogan was that you should drink a Dr. Pepper at 10 a.m., at 2 p.m., and at 4 p.m. because those are the times of the day when people have lulls in their energy levels. Now, I have to admit, I was a little surprised that they were suggesting 3 sodas a day. That feels a bit extreme. But what I did find out, though, was that when they were making that claim or that sort of suggestion, the Dr. Pepper bottles, if you look closely at the bottom of this one, were 6.5 ounces. Today's Dr. Pepper bottles are, 24 ounces or whatever. So, 18, 19 and a half ounces a day isn't awful, but I do think I did find that fascinating. And that uncertainty, that simple thing had me on a quest to figure it out. Again, it's that innate desire. I had to go resolve my own uncertainty. And that's what I want to have happen in the math classroom. I want to create spaces where kids can be curious about things. They can chase their own desires and they can think about the things that they're interested in. And what I'm going to do over our next sort of 10 minutes together is share with you sort of like what I'm calling the 6 key components to curious classrooms. And in those 6 components, we'll talk briefly about each of them. But I have to start by saying curiosity and creating curious classrooms is not a checklist. Okay. So even though I'm going to give you 6 things, I have to urge you to play the long game, which is this isn't about like if I go do these 6 things, my kids are going to be curious. It might help and it might spark some, but it really is like it's a thing that we do that we have to embrace curiosity as a whole, right? It centers the humanity of young people. It puts their humanity at the forefront. And then if we're able to create cultures and safe spaces for learning where each and every kid's ideas are valued, then we're working on that sort of long game of creating curious classrooms. So again, I'm going to share 6 ideas with you, but I don't want you to see them as a checklist that like you go around and look for these things in classrooms because it's not the way curious classrooms work. It's not the way humans work. But let's jump through a few of these. The first one I want to share with you is this idea that we should be providing choice and autonomy to our young people, right? That is first and foremost the way that we're going to get kids curious. When they have ownership over their learning, when we invite them to make choices and take charge of their learning, they're going to be more invested in it. When they can get involved in play, in true sort of play in the way that we're talking about it, it is magical at getting them curious. They want to stick with it for a long time. And then finally, this sort of idea around trust. We have to trust our young people. We have to trust them with the math. We have to trust that they are going to engage in the work that makes sense in ways that make sense to them. And to highlight this, I'm going to tell you another quick story about one of my brilliant second graders. This was the 2020 school year, I believe, maybe 21 school year. I was teaching in a multi-age classroom with first and second grade students. And in my classroom, we had 45 minutes every week of explorations time. And during explorations time, kids were allowed to explore anything they wanted to explore. Now, that can seem a little scary, I think, as to where they might go. I can tell you my experience was so often kids would be exploring things that we had already started in other parts of the classroom. Maybe they were still working on a pattern that they worked on earlier in math, or maybe they were going back to a book that they read and doing a bit of research about something in the book. And other times they would just do something completely that they wanted to do. It would just be like, all right, I'm going to go explore this thing. And the story I'm going to tell you is about one of those days. This is where I found Klein. Klein was on the carpet with all of these hexagons around her. And I came up to Klein and I asked her, Klein, what are you doing? And Klein said, I'm trying to find my perimeter in hexagons. And I thought, this is the greatest thing I've ever heard. I was so fascinated by someone's perimeter in hexagons. And here's what happened. During this time, I'm going to skip to the end of this. Just a little bit later, I came upon Klein and her partner, Kanika, and this is what they were doing. Again, these are beginning of the year second graders. They're not primed to be adding 5 2-digit numbers at this point. But because this was Klein's problem, they ended up doing this. Let me tell you how they got there. When they stood up, we had this what kind of looks like a chalk outline of a child here, but they were trying to count the hexagons and they kept getting stuck. So they'd start counting and they'd lose track. And so Klein said maybe we should like mark off groups of 10. And then they tried that and it was not going as well as they wanted. So they ended up marking off these groups of 30. I've just sort of like written some things on the screen here so you can see, but you'll see the start. And then that first 30 is that red hexagon up in the top, or sorry, red trapezoid up in the top left-hand corner. And then there's another 30 where they put a square on, and another 30, and then a 20, and then a 13. And that's where those numbers came from. So this problem, if I would have put this problem up on the board and said, solve 30 plus 30 plus 30 plus 20 plus 13, maybe they would have done it. Maybe they would have been engaged with it. But because this was Klein's problem, they were more invested in figuring this out. They were willing to work past those problems they were having with counting and kind of getting lost in all there and thinking about other ways. And that's what real choice and autonomy can do in the classroom. It gets them curious and it keeps them curious. Let's keep moving forward. Our second key component here. Thanks, Jessica. I'm glad you're on board with that. We have to normalize and model and celebrate uncertainty. If curiosity is based on us being uncertain, we have to create spaces where uncertainty is okay. Now, I'm not going to tell you my pull-up story. I don't have time for that. But if you haven't listened to Mike and I's podcast, it's called the Educators Podcast. I've actually told that story twice now on the podcast, but it is deeply connected to this about me modeling my own uncertainty and my own inability to do a pull-up in front of young people. But we're going to come back to this idea of uncertainty when we get to our first math task. But I do just want to acknowledge that this is a key component, normalizing, modeling, and celebrating uncertainty in our classroom. Third key component of curious classrooms is that we have to focus on student thinking. We have to allow a focus on ideas over answers, on listening to the way that kids are thinking about it, on creating spaces where maybe we're using the 5 practices to foster discourse. Maybe we're using, Cassia and Christie's book called Hands Down, Speak Out Conversations, but we're using frameworks to increase discourse in our classroom. We're going to use number routines, whether those are number talk images or a number talk here that you see in the middle. And we're going to be inviting alternative perspectives. So we want to make sure that we are having each and every kid's voice heard in our classroom. And that includes so many kids who have been historically marginalized in the math classroom, Black and brown students, students from the LGBTQ plus community, multilingual learners, right? We want to make sure that those voices and those perspectives are not only shared and highlighted, they are seen as central to our classroom. And that's because when we get different perspectives in there, and this is where we're going to get to our sort of argumentation and judgmental piece here, when we get different perspectives that don't align with what ours are, we become uncertain and then we become curious, right? When Mike presents something that I haven't thought about before and I have to think about that for a second, now I'm more willing to engage and be a part of it because I'm curious about it. So that's why other perspectives are so important. That's why, showing different representations and strategies for solving the same problem are so important to get kids curious. Okay, let's keep going. Our fourth key component here is embracing our role as a listener. I've done a lot of thinking and talking over the last 15 years about my quest to become a better listener, and I'm still working at it. It's really hard for me. I love to talk. I really do, as you can tell in this experience here. But really trying to figure out how I can embrace my role as a listener. I got 4 quick ideas to share with you here. We got to ask questions we don't know the answer to. So things like, what do you notice? What do you wonder? We're asking kids that because when we do that, I'm going to be more willing to listen to them. And when kids felt listened to, they're going to be willing to take risks, be vulnerable, engage in that uncertainty, right? So I want to make sure I ask questions that I don't know the answer to. Got to spend less time at the board, right? I'm not saying we should never be there, but there's a power dynamic that's set up when we're standing at the board, and that is the sort of it communicates that I'm the one who holds the answers, and everybody else who's sitting down is there to learn from me. So less time at the board. More time for student talk. We have to be intentional about how we do that. Again, whether you're using 5 practices for orchestrating discourse, a great way to get kids talking in your classroom and being intentional about where and when we do that. And then finally, providing pause, making sure that we create space where we are not talking over kids. And this is one of the harder places for me because when a kid says something really brilliant and exciting, I just get so excited myself and I want to start talking and talking for them, right? Because I'm so excited about what they're saying. So really being intentional about where we stop and when we stop and pause, I think is really important. Okay, we've got 2 more components and then Mike's going to jump in and talk about argumentation. This next to last one, the 5th one here, is that we want to use math tasks built on cliffhangers. In that same book, The Hungry Mind, that Susan Engel wrote, she talks about, it's not a book about school necessarily, it's more about human curiosity and what happens in our brain. But there's a section on schools, and one of the things that she talks about is that we can leverage this idea of cliffhangers, right? You know exactly why you keep watching the next episode of a show on your favorite streaming platform because the episode ends with a cliffhanger. You're just gonna keep watching because you want to resolve that uncertainty, right? When a movie ends and it's gonna keep you get you ready for the sequel, right? There's a cliffhanger there. Books chapters almost always end with some sort of uncertainty to make you want to keep reading, and we should leverage that in the math classroom. We should be creating tasks that have cliffhangers. I got a couple of ideas here for you. I love story-based tasks. If you haven't ever seen Mike and I think about this bike lane here in Seattle, we've had a lot of fun talking about that. You see Mike looking up down there at the bottom of that circle. But it's a task based on a story that we're telling, and then we get invested in it. I think slow reveal graphs might be the one of my favorite things right now. As we think about tasks built on cliffhangers, you're sort of slowly revealing information so that kids are hanging on for what's coming next, right? So instead of just starting with the entire data representation right in their face, you start with something hidden from them, and then at that point, you then reveal a little bit more and a little bit more, so you get that cliffhanger right there. And then finally, of course, I'm sure most of you in here are familiar with three-act math tasks. But three-act math tasks literally are leverage the cliffhanger at the end of Act One, right? Or in the beginning of Act One. You're sort of left with a moment of like, what's going to happen there? What now? I'm curious, right? So using cliffhangers, and Mike and I have done a bunch of work. You can find it in our Friends of Fun Education community, but we've done a lot of work on how to adapt tasks to be built around cliffhangers. That's not today's talk, but if you're interested in that, we'd love to continue that conversation. And then our last key component to creating curious math classrooms is that we gotta facilitate debates around math ideas, and that's where I'm going to toss this over to Mike as he talks to us a little bit about debate and argumentation and those ideas. So, Mike, it's your turn. I'm going to take my spotlight off and put you on. There you go.
All right, cool, man. I appreciate it. So I'm now I've got the spotlight now.
Looks like it.
All right, cool, man. All right. So thanks, Zach, for setting up the curiosity piece. It is like we both love it. There's so much power in the math curiosity. And now I'm going to come in as the evil one to bring in the judgment piece. But it's like, but I do really believe, like Coach Beard, naturally skeptical here, but I want to talk about judgment from a good standpoint. This isn't like Mean Girls judgmental. We're talking about making, like in math, like we actually want students to have some level of judgment, that we want them as they start to notice some regularity to have some conviction to say, I think this thing's always going to happen. And then when they make that judgment, that I feel like every time you double one factor and half the other, the product's always going to be the same. Like that's a judgment. That's a statement that students will make. That's the perfect place to start to construct really good arguments. Now, I've found working, because we work with preschool through high school math classrooms, like we're in class teaching, and I find math argument and teaching kids the ingredients of a really good math argument can really set kids up for success and for and just enjoyment around the math class. So we're going to dig into that for a moment. Let me go to full screen for a moment with the slides. And I'm going to start by just defining what a high quality math argument is. So the definition that I really like is that a high quality mathematical argument is an argument that shows that a claim must be true. It like leaves no room for doubt at all. The chain of logic leads the reader or the listener to conclude that the author, the student, whatever, that their claim is true. And to have a solid argument, it really takes three key ingredients. Technically, there's a fourth one, but for the purposes of elementary and middle and high school, we're going to stick with just these first three. The first one is a claim. That's actually a claim is just it's a mathematical statement that one believes might be true. Doesn't mean that it is true. It just means that we believe it's true. And so this is a claim from a second grade class, actually my second grade class when I was still teaching. And my students were exploring regularity with subtraction and noticing what happens when you add one number to the minuend and one number to the subtrahend in a subtraction problem. And they started to notice that the difference, the answer is always the same. And so a claim, one student, or there's a group of students, but one student wrote it, said, when you add one to the first number in a subtraction problem and one to the second number, the answer is the same. Now, right now, the claim itself, like we know our math skills are strong enough to recognize, like, yeah, that claim's true. But if you didn't know that, if you were another second grader who maybe hadn't noticed that regularity, would that claim alone convince you? Would you be moved by that? Like, so a student made a judgment that this is always going to happen. They've made this claim, and you'll notice that the claim by itself probably doesn't sway someone who doesn't see the pattern or doesn't notice that. So that's why the other ingredients are important. So the next part of a good mathematical argument is the justification. And that's the reason, it's the warrant, it's the sort of backing up your claim, your statement. And so in this case, a different group, we were working on this as a class. So you're going to see student work samples, not one, in this case, one student having all pieces of the ingredients. We were sort of co-constructing this as a class. But another group's justification for that claim, because they all had variations of that same claim, was that the space doesn't change, meaning the space between those, whatever the two numbers are. And you'll notice that on their justification here, their number line, they didn't put any numbers because they wanted to show it worked for all instances. And so the space doesn't change. Therefore, that's why it works. So when you add one to the first number and one to the second number, the answer is the same because the space isn't changing at all. And then the last piece is the evidence. And so the evidence is used to support the claim and justification. And so in this case, and I'll just kind of illustrate it right now. So this happened on my smartboard at the time. So I was only able to screenshot it and not get the animation. But they originally said that the difference or the answer of or the difference rather between any two subtraction or any two numbers is the answer of that's the answer. It's like the distance between any two numbers is the answer of a subtraction problem. And if you add one to that first number and one to the second number, they said it's the same distance. And so they drew this like red one here. And then because it's a smartboard, they were able to grab it and slide it back and forth. And they said it just slides, but I asked them to write it so I could screenshot it. But if you imagine now that someone's saying the claim, if you add one to the first number and one to the second number, that the answer will stay the same because the distance doesn't change. And they're illustrating it with this evidence. You notice now how much more convincing that argument is. And so what this helps is for kids to articulate their math argument in a way that really builds in all these components. But I want you to consider, in order for these second graders to construct this kind of argument, how much math thinking did they have to do? How much understanding of subtraction did they have to have? How much understanding of the structure of our number system do they have to understand? And you realize that doing this work is actually doing some heavy, heavy lifting for a lot of the standards that you're doing. And this works. We've done this with kindergarten. We've done this all the way through high school. Obviously, with high school, you get to more sophisticated evidence. But yeah, I love seeing the reactions there. But these are my second graders. This will blow you away to what they're capable of. But part of it is helping them to recognize that it's not just show your work. That's sometimes I think sometimes the work that kids will work on a problem and then they're asked to show their thinking. And so it feels like they're being told to do that. So they're proving that they did their work. They didn't cheat and stuff. If you frame it to, I want you to show me a good math argument for why your answer is right. It reframes how why they're having to show the work on their whiteboards or their journals or whatever it is. And so this is just one example. I want to show a high school example as well, so you can see how this all kind of plays together. But for high school, so in a ninth grade class, we love Fawn Wynn's visualpatterns.org. So this is one from her. We presented this to a group of ninth graders, and a student, this was an individual student, made a claim because what they were there. I'll go back to the directions here. So you've got this pattern that's growing so they can see step 1, step 2, step 3. And they were asked how many dots would be in step 43 and can they make a general claim about this pattern? And the teacher was really trying to get the students to start to generalize a little bit more. And again, getting to this math argument. So there's a lot of ways you could think about this. So what was great for this particular task is, I'm going to just show you one student's argument, but I've got a bunch of these, is that, so this student had one way to look at it and made a really compelling argument. And then other people saw it completely differently, made a completely different argument with evidence and all of that. And then the conversations around what was the same with the different formulas and the different ways of seeing it and what was different. All this math came popping out of it. So just watch the math that comes out just from this one. Even if you don't teach high school, you're going to start to see some amazing things from putting all three of these ingredients together. So here we've got, she says, the number of dots will always be double the step number times the step number plus one, and then add three. Now, again, notice the claim. Now, some of you are like, yeah, I see what she's cooking. I got it. Some of you are like, I have no idea what that means. That's a lot of words at once. So the claim is a good part of it, but you might need some reasoning and you might need some evidence that would help build some clarity here. But it's this is the starting point here. So the justification is that each step, and for those who don't teach like patterns and things like that, a step means like, this is like, let me go to drawing here. So this is step one, like the pattern. And then as it grows, this is step two, this is step three, and it just goes on and on and on. So the, when they're asked to think of step 43, like they can't draw it out. They've got to really start thinking abstractly with this. So she said each step makes two arrays that have one length that's actually equal to that whatever the step number is. So if it's like step 27, that one of the length of that array is 27. And then the other length is going to be equal to that same step number 27, but plus one. So it'll be a 27 by 28. And there's going to be two of those. And then there's always three dots left over. And so that's the justification. And then finally, the evidence. And this is what she put forward. And she kind of has, I'll just kind of doodle a bit on her thing here, but she has like sort of tested it out with a smaller step. And then she sort of started to generalize it a bit and then getting more into like, think about it more algebraically. And then she was able to sort of do like a substitution to kind of get like what step 43 would look like. And so watch what happens when we put all three ingredients together. And so here you've got, and I'm going to illustrate it. So she would talk about this as she had this up on the document camera, was like saying that the number of dots will always be double the step number times step number plus one, and then add three, because each step, in this case, step two, makes two arrays, this one and this one, that have one length that's equal to the step number. So notice that this has one length is but two, and this is step two. So we got, and then the other length is going to be equal to the step number plus one. So this one is 2 plus 1 is 3. So we've got a 2 by 3. And then if you look here, it's the same thing. Here's step 3. This is a 3 by 4. And then step 4 would be a 4 by 5, etc. So so we can see there's that one array, there's the other array. So the number of dots will always be double the step number. So you just double these two arrays there. So that's the 2 times the step times step plus 1. And then every time you do that, there's always these 3 colored in dots. And so there's your plus 3. And so if you notice, when you put all 3 of those pieces together, how clear the math thinking is. So even if you don't teach algebra, like that, you're able to now, like, you can connect to that. It's like, oh, I wouldn't have seen it that way, but it makes a lot of sense. So this is that first part of judgment, where it's actually not about critiquing. It's just about making you make a mathematical judgment. Like, that's how she saw it growing. She then made a judgment that this is what you would do for the formula, and that's what it worked. Other students, it actually envisioned like a square going around the whole thing and then sort of remove pieces. Again, it's pretty wild. So this is the first part of math argument. You put those 3 things together and you've got great math argument. You don't even have to have critiquing in, but let's kick it up a notch and let's do some critiquing. Let's get into the pushing back a bit. Now, this takes some finesse, because the idea here is we still want them to be curious in their critique. We want them to wonder, not do a whole, like, you're wrong, I'm right. It's not about that. This is like, you're trying to help them deepen their thinking a little bit. So I'm going to start with something. This is from a 4th grade class. And you might think 6 plus 0 is, why would that be a 4th grade class? Sometimes when you're doing math argument and trying to understand the nature of the way certain numbers behave, working with small numbers allows students to have their brains mental energy to focus on the really complex structural elements. And so in this case, we were looking at the behavior of addition, subtraction with different numbers. And there's a pair of students that were looking at what happens when you have zero, when you're adding zero. And one student just said, this was her statement: adding zero to any number doesn't affect that number. Right? Would you all agree with that? Put a yes or something in the chat if you agree with that statement. Adding zero to any number doesn't affect it. Right? Look at all the thumbs up. Okay. Now, her partner critiqued this. She's going to make an argument. Now, I'm going to switch my microphone for a moment just to make sure we can hear this. I capture it. It's very brief. But I want you to hear her voice, and I've subtitled it, and then we're going to analyze her thinking. But give me a moment to switch over to mics, and I want you to see if her critique pushes your thinking a little bit.
Some you have x to zero, it's still equals 6, but it's affecting it by nothing. And affecting something by nothing is still affecting it by something, but something's not.
All right. I want you to think about that. I'm going to put her quote here. So she said, her partner said, if you add zero, it doesn't have any effect. And she said it does. She said, if you have 6 plus 0, it still equals 6, but it's affecting it by nothing. So she's saying the effect is that it's affecting. I mean, I'm not even going to try to paraphrase. I'm going to say her words, but it's affecting it by nothing. And affecting something by nothing is still affecting it by something, but the something is nothing, right? Like, tell me that doesn't just blow your mind around. Like, and you may say, like, oh, like, I don't know if I like mathematically agree with that. But here's the thing. We talked about that. That was so interesting to think about that. And zero became a really interesting thing. It wasn't our whole lesson for the day. I don't want you to think like this is all we do. We were still focused on math argument and generalizations and things. But there's some power when we push on some of the thinking and some of the statements that we make. Even if we, at the end, it's like, that either one of these things is correct, right? It doesn't have a change, so we could say it has no effect, right? Or it is affecting it, but it's affecting it by nothing, which is the same thing. It doesn't really matter in some of these cases because it's just about like thinking about the zero. Like anyway. So I'm gonna just encourage you to think about weaving in these 3 ingredients, making them, and you can rename them for, I mean, I find they work at all levels. I might say instead of justification for primary, I call it make your claim. Claim's fine. And they'll say, give us your reason instead of justification. And then evidence. I still use evidence. And so those 3 work really well, and they work all across the grade levels. So, and then if you want to weave in the critiquing, the only suggestion I do is it's all about coming from a good place, and it's about pushing our understanding and not pointing out errors. Like it's and if there is a mistake, that we can point it out in a way where we're just asking, like, I'm wondering if that's right, or I'm wondering why we got different answers here. I'm wondering if there's one right answer we might look at. There's just ways to frame things so that students can still point things out without having the class feel like there's any kind of like mean judgment going on. So with that, I'm going to turn it back over to Zach to have us kind of look at ways that you might do this in a more playful way. And then we're going to look at wrapping things up a bit. So, all right, Zach.
Yep. All right, we're just going to check in real quick here. We're a couple of folks, Mike, I don't know if you saw that we're having a little bit of trouble finding you and I. So we're spotlighting our videos. If for some reason you unspotlight us, you can pin our videos, or you can just change your view in Zoom to speaker view to see us, whichever one of those works for you. But I just wanted to check in and make sure everyone was good with that and weren't having issues seeing slides or in that sort of way. Also, Mike, you'll be very happy to know that there's a lot of conversation about your shirt. I'll let Mike tell you all about Severance in the chat box. Pretty fun stuff going on there. But what I want to do now is take us to one of Mike and I's longest running and deepest feeling debates or arguments, whatever word you want to use. We are on opposite sides of this conversation, and that is around stairs. I know many of you have seen some of the things that Mike and I have been doing on social media or in sessions around counting stairs. But I'm going to kick this off by showing you a short video of Mike and I in Chicago at NCTM and NCSM back in 2024, where we first started counting stairs. I just have to say, this all stems from the idea that literally every young person I've ever been around, kindergarten, first, second, third grade, they love counting stairs. It's like a thing they almost naturally do. And little did Mike and I know how much the stair debate was going to become such a big thing. So I'm going to share my screen with you here. We're going to go this route, make sure I share my sound so that you can hear Mike and I debating these stairs. Oops, let's see here. It can't be 10. Show us 10. Let me see 10.
All right,
okay,
ready?
here we go.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10 stairs. He's right, everybody, right? Well, Mike, I'm going to try and prove you wrong here. So
right.
I'm going to do the same thing you just did, but I want you to count with me this time. Okay, ready?
Yep.
Here we go. Ready? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's the 9th stair right there.
What about this?
That's just a flat ground. It's not a stair. So, we're going to make a case here, Mike. We got a test group of about 20 people here. Drop in the chat box right now your gut reaction. Are you team Mike? Are you team Zach? I'm going to show you a rendering here of the side of that staircase that Grace wins. She was in their first. Oh no, she wasn't. Shelby was. Never mind. I'm not taking the first argument with Shelby. Here's the side of that staircase you can see, and you can take a look at what you want to count. The question is, how many stairs do you see here? And here we go. We're getting some good stuff. We're gonna have to. Man, that's a lot of 10s, Mike. That's a lot of 10s. Laura with the
Always
11.
team Mike.
Here we go. Laura with the 11, bringing the big guns out. You guys, I did this yesterday in Virginia at the Virginia Council of Math Specialists. We had a room probably about this big, couple hundred people in it. And for the first time, Mike, I haven't even told you this yet. For the first time, someone gave me the answer of 1 and said, there is 1 set of stairs. And I had a big unit chat moment of like, okay, that's a new answer there. So like every set of stairs is just 1. We don't have to argue anymore. Let me just quickly run through these 3 sort of ways. Here's Mike's argument, right? Sort of as we move up, we're counting each of those movements going up. One might argue that's a step versus a stair. That's for another day, perhaps. My argument here is that that top thing is different. Just like Lorraine just said, 9 steps and 2 landings. Those feel very different to me than the thing at the top and the thing at the bottom. And then I think Laura and a couple other folks mentioned 11. If we're going to count that top thing, maybe we got to count that bottom thing as well. Mike and I have done this with just hundreds of teachers and probably a couple hundred students as well. This is a really great first, second grade task. They will debate this forever. Lori Price and I, many of you know Lori Price, was in her classroom this time last year, and we posed this problem to a group of first and second graders in a hands-down conversation. Lori and I stepped to the back, and for 22 minutes, these kids debated this idea. They went back and forth and back and forth. I'm going to share a couple of their ideas with you. One argument from a young person was that you have to count each time you raise your foot. This is sort of like, I think what Mike's argument is. There's a couple of other variations of this argument, right? One of them is, and I don't say this lightly, I say this with a very deep heart, which is a teacher who taught at a school for the deaf and blind said if I told a student that there were 9 stairs, Zach, they would trip over the last one. So like there is that. I understand that case. The other side of it is if I can go back to this for a second here, if we're just looking at this, if the opposite of that argument is if this were a house and there was a second floor up there, that landing is already there and there's a bottom floor, there's 9 things that you would build in between the 2 of them. So as you're building the staircase, you wouldn't have to build that top thing because the floor is already there. Oh my gosh, Dory's bringing up toilet paper. We're getting deep here, you guys. This is great. I love this. So a couple other arguments from kids, and then we're going to play with one other math idea here. You're welcome to put your case and your claim and all of that in there in the chat box right now. Another great argument from a young person is you don't count the top platform or the ground because you put 2 feet on those, and stairs are something you only put 1 foot on. So you kind of make this sort of like movement up the stairs. I did have a student who said that's true, except for if you're little, you have to put 2 feet on every stair. So maybe the answer is 18 or 20 or 22, depending on how you count. But now we're up to at least 7 or 8 different answers here. There's something about what we're counting to. So are we counting this corner? This is the language that second grader use. Are we counting this corner or are we counting this corner? Which one of those things are we counting as we go up? Top part's not as big. It can't be a stair. Some kids have to put, that's what I was mentioning earlier. Some kids have to put both feet on those. I got to show you a couple more things. Mike mentioned the Debate Math podcast, which Rob Baer and Chris Lesniak are the hosts of. Mike and I did a series of minis with them. One of them is about us counting stairs. You can see my hand motions there. Generally, when someone's counting these things, they're sort of making motions there. Recently, someone on Instagram sent me this. You guys know about witch stairs? Whew, man, this one hurt my brain a little bit. These are what are called witch stairs, and apparently the theory behind them is that they built them because witches would wear a dress and they couldn't see their feet. So they couldn't walk up these stairs. And so these were built. And at the top of those, if you look at the one in the middle, that landing up there is very different than these things here. Um, I, I also think there's a flaw in witches' stairs because if I know anything about a witch, I think it's that they can fly. So I'm pretty sure they could just go up the staircase on their broom. I don't know, but this is the real thing that existed in this world. There are a couple of other really fun ambiguous debates happening right now. Shelby Strong's in the room. Justin, and her and Justin, and a lot of other folks, and oh, I can't remember who else, but even John and Kyle, you're here talking about sandwich chat around what makes a sandwich. Right now, this month on Instagram, our good friend Chris No is crushing our brains with vehicle chat. Is what things involve a vehicle, and then as I mentioned earlier, Shelby and I have a lovely long-standing debate, which many of you have been a part of around trapezoids. And yeah, I put my case up there and not Shelby's. It's fine. You can be team inclusive or you can be team exclusive, but that's another really fun debate where there is some ambiguity in there, right? There's ambiguity around what we're talking about. The last thing I want to say about this is that while that conversation, I think to some people might not feel, really mathematical. I'd like to make the case that what we're doing in those debates is deeply mathematical. We are saying, I believe a stair is this thing, and now I'm going to base every staircase I ever see around that definition that I come up with, that I'm adopting, right? Or if a vehicle is defined as something that transports something else from point A to point B, we have to now make answers around, is this thing a vehicle, right? And the quintessential one around that's like a merry-go-round, right? Is a merry-go-round a vehicle if it really doesn't really take you anywhere, but you're moving? So you're doing this deeply mathematical thing, right? Let X equal blank. Everything else I'm going to do in this proof or whatever is based on that statement, right? That's what we're doing here, right? So I think this is deeply mathematical work that gets us involved in some really interesting debate and argumentation. Okay, Mike, I think we got one more task for them to play with in our last little bit of time here. So I'm going to remove my spotlight and pop it back over to you.
All right. So, and people have been asking about the slides. And so we're going to do a little two-parter thing. So I just dropped a link in the chat. If people wanted the slides for the session, you can put your information, we'll get them sent. You'll get a set of my slides right now. That's the one thing with Zach and I working on different sides of the country is, and what we'll do is we'll have your information. So what we'll just send another round with the second half of Zach's slides if folks would like those as well. And I appreciate all the support for Team Mike on those stairs, by the way.
Oh, so, gosh.
All right. So here's what I'm going to do. I'm going to go ahead and spotlight myself for everyone here and just get into the last bit. I wanted to have you have an opportunity to try some of this, being like getting the arguments here. I'm going to show you one other thing that you can bring into your classroom. I love this framing that we use sometimes about the different ways of knowing and convincing. And so in the field of mathematics, there are different ways of coming to believe that a generalization or an idea, whatever, is true. The first is accepting it just on authority. This is like the trust me bro method, right? Like, oh, okay, Dr. Flynn said that that's true, so I'm going to just trust it, right? That's the least powerful, right? But it's one, right? We could just trust an authority. It could be a student, it could be a teacher, whatever it is. A more convincing way would be to test it out a bunch of times. Just try with a bunch of examples. But we know that just seeing some correlation doesn't always mean causation. We can't always make a claim that this will always work if we're, because there could always be an instance where it's not true. But for young kids, particularly at the elementary level, is number 2 is really that's does it for them. They're like, yeah, I've done it 4 or 5 times. That's enough. We want to push into this next spot. I think 3 is where elementary and middle can live for quite a bit. So high school can as well, but obviously in high school, we're going to get to 4 as well. But 3 is applying mathematical reasoning based on a visual or physical representation or story context. So going to the different ways we represent math ideas. And we call this representation-based argument. And this comes from the work of our dear friends and colleagues, Deborah Shifter, Susan Jo Russell, and Virginia Bastable, who've done lots of work in early algebraic reasoning, looking at elementary and middle school thinking with this. And the final one is proving it using algebraic notation and the laws of arithmetic. And so for today, you can do any of these that you want. But I'd love for you sort of as like a pillow problem, because we won't have time to dig in deeply with this, but I'm going to give you the things that you need to play with the math. And you could also use this with students if you want. But we're going to look at operating with even and odd numbers. And if you wanted to, with if you teach middle school, high school, and you want to go farther, like for operations here, we're going to do just addition and subtraction. I was trying to get something that would be accessible for a broad audience, but you could look at multiplication or division. You could also look at other domains of number. Like you can kind of play with this. The same way we explore this, you could explore it with any idea. So for this, I'd like you to think about making arguments that use like diagrams, cubes, other visual representations. And so one thing you could explore is to think about what happens when 2 odd numbers are added. And is so right now in the chat, we could just start together. So what would happen when 2 odd numbers are added? Even, right? Pretty. And so is that true for all pairs of odd numbers? And how do you know? So these are some things to consider. And then as we think about this, this is where we're going to get into the math argument. What kinds of arguments can you make to show that your generalization is always true? So it seems like everyone's saying 2 odd numbers are always going to be even. So what's the argument? Why is it, right? Now, remember, the argument is not just, well, yeah, because like Mrs. Swanson told me in 2nd grade, so I remembered it. It's why? Why is it that 2 even numbers or 2 odd numbers always result in an even number? Why is that? And so then you could start to think about how would you then represent that? And so I'm going to drop in the chat now another resource for you, which is a slide deck that has virtual manipulatives in it. So in the chat right now is a Google slide deck. It'll ask you to make a copy. It's probably going to bug out for a little bit because of so many people here. That's just be patient. It'll come around. But it's going to have these same questions and prompts, but we're going to have some draggable like cubes, if you will, that you can play around with. Now, another one that you could look at is this one. What happens if you multiply 2 odd numbers? What happens if you multiply 2 even numbers? What happens if you multiply an odd and even number? And is this true for all pairs of numbers? And how do you know? And again, what kinds of arguments can you make? And what to show your generalization is always true? What representations for odd and even numbers for multiplication do you call upon for your arguments? And like what definitions of an odd and even number are you using? So using those ingredients, coming up with your claim, having a justification, and then showing using some representation, show us why that would be true for all numbers. Yep.
You got a couple people that are requesting access. You might need to change the sharing settings on that
slide.
Oh, sorry.
You know why? I duplicate it. Oh, rip my inbox now. Yeah, let me, okay. No one else requests it. Let me just quickly change this. Oh my goodness. Because I've switched from my
Mary
laptop.
Was ahead of you. Mary just said she's not going to request it, so you don't have 200.
Oh, thank you. All right. Now, if you all refresh it, yeah. I can't wait to see. You have 700 notifications. Okay. So here's what we're going to do. I'd like you to just take a moment and just play with it right now. And feel free in the chat or on the microphone to just make it like you can play around with one of your arguments. You all can be in different places. And if it comes for like adding odd numbers, you can also like explore like what happens if you add an even number of odd numbers. or an odd number of even numbers or any of these things. Like play around with that. And then look at this, like Dory's got one. If you remove one from the first odd quantity and move it to the second odd quantity, the resulting values are both even and they will both be paired up, which is using, it looks like your definition is pairs for that, right? Combining them so that total stays paired up even. Nice. And now Shelby's got one, like showing it a little bit more algebraically here. So 2m plus 1. There, now the chat's got to start getting away from me. So, but there's lots of great thinking on here. And feel free during this time, if you want, just in the last couple of minutes, because then Zach and I are going to just share some ways that you can also stay in contact with us, is read through some of the arguments that people put in the chat and then see if there's like, can you think of anything that like questions we might have? Is there anything that you're curious about? Like, would that always be true? Is that claim totally right? Will that always work? And that's the space where we can get into some really interesting work. What you're going to find here, and I could see in the chats people's reactions just looking at those second graders with their subtraction, and then looking at how that ninth grader was looking at that visual pattern and her justifications, and then that fourth grader with the zero is something to the nothing and all of that, and then even looking here, you realize all of this. There's such rich, powerful mathematical thinking, and my favorite part of all of this is that all those rich ideas come from students. When you do this work, it's their voices. It's not me. I'm asking questions. I'm saying, how else could you show that? And what's another thing you might say? Is there another representation you might use? I'm the facilitator. I'm the MC of the event. They're the stars of the event. And in doing that, it elevates student voice. It elevates students' confidence, and it elevates their thinking and learning, because this really helps us to make sense of the math. I want you to think about my second graders with subtraction. Like, in order for them to make those kind of generalizations, they really had to understand the nature of subtraction. That ninth grader really had to understand the nature of the patterns and all that algebraic thinking. She had to have a good, solid understanding. It's a really fun, engaging way to build that. We really encourage you to try it with your students. I'm going to turn it over to Zach now. And Zach, maybe we can just do the double spotlight, and then we can let them know what else we got cooking.
Yeah, I just dropped a link in the chat box if you're interested. Mike and I have recently taken our Friends of Flynn Education community and made it free for everyone. So if you're interested in joining us in a space where we're working on, I mean, honestly, if Mike and I tell the story quite often, but like the impetus for this was like losing Twitter was deeply hard for both Mike and I, and for so many people that were part of a really robust math education community. And so we started to think about like, how can we try to recreate some of that in a new format? Because I don't get me wrong, I do love Blue Sky. I spend time there, but there's something about it that feels like we're trying to just kind of do the same thing. So how can we try to rebuild community in ways that are a little bit more up to the next level? So we've got once a month live math play dates. We just hosted one this last week, earlier this week, with Howie Hua. He was our host. He brought a problem for us to do together where we just play with a math problem as math learners. We focus on ideas over answers and representations, looking at representation strategies. We do an interview once a month called Voices from the Field with a colleague of ours that you can join live. We release those later on our Educators Mathcast podcast, but this is a chance for you to join those live and hear right from them and get all the unedited version of those podcasts. Well, Mike and I are also recording some sort of like short 10-minute videos, one for teachers, one for leaders, to kind of share some ideas with you all each month. So you'll get access to all of that, plus lots of ready-to-use tasks if you're interested in that. Come join us over there. It's a really lovely community. We've been having a lot of fun with that, Mike. And like I said, I put the link in the chat box. I also dropped my slide deck in the chat box, Mike, just so you know. So I just condensed it, so it's right there for you. You can get Mike's by filling that one out. Mine's in the chat box for you. And that's all we have. Mike, anything on your end before we let him get out of here?
No, just we're super excited that you all came here. It really means a lot to us to see so many of you come and join us and support this work and maybe learn some things from us. We certainly like to learn things with you. We would love to have you join our community. Like, it really is like, this is a place for us just to collaborate and play. It's we love our math peers and really appreciate all that you do. So let's be curious and judgmental together.
Thanks, guys. Thanks, guys. Everybody, as you say your thank yous in the chat, do us a favor and drop your big takeaway. Like, think about back to the nuggets, the inspiration, the ideas, that maybe the practical, activities that we talked about here, and drop that there. Let Mike and Zach know what was the big takeaway for you. I know that I always like to see that. I know that they would, and it's great for you to reflect on what was your big takeaway here today, and we want to, you want to do that so that we don't walk away going like, well, what was it today? Like, you center on it, and that can make it more impactful for you. So do that in the chat. We'll let that kind of flood for a little bit. I do have a couple of reminders here as we kind of end this session into the next session. We do have an upcoming building capacity series that's happening next month. It's hosted by Yvette Lehman, one of the coaches here at Make Math Moments. It is a completely free two-part series on making sense of fractions. We encourage you and your teachers that you're working with or your colleagues to sign up completely for free. It's makemathmoments.com/training. That's one of the events we have next month. We have an event like that every single month. We host we call them the Building Capacity series on helping teachers strengthen their own capacity around mathematics. So that's one of the reminders here as you're kind of populating your big takeaways there for Mike and Zach to kind of look in on. One other reminder here is don't forget that your certificates will be updated throughout the weekend. So keep an eye on that. Keep an eye on about a generator from us coming out either tomorrow afternoon or into the next day on Monday. So just that reminder. I know that we've got a number of sessions here that are still ticking on today and Saturday. We've got another full day tomorrow, and your free access is will end at the end of tomorrow, and we're looking forward to continuing that learning. But Mike, Zach, thanks for your time, your dedication. Did you guys see some big takeaways in there? Anybody you want to call out?
Oh gosh, I hate to call up just one. I'm just like, but I am loving reading. Like, they really some key ideas that we were hoping people would walk away with. We're seeing that, so it really makes us happy to see that.
Awesome.
Yeah,
awesome.
I just saved the chat so I can go back to it. But anyone who is Team Zach is my highlight. That's all I'm going to say.
those three people.
Those few. Yep.
Awesome. Okay, everyone. Thanks for joining this session, and we'll hope to see you in another session today or tomorrow. And we'll talk soon. Take care. Thanks, guys.
Bye, everyone.
Bye, everybody. Thanks, John.